In this video, I'm going to cover the 5-0-Chem online final exam practice quiz that is going to cover heat. So in this first question, this one's pretty straightforward. Temperature and heat are exactly the same thing, and that's going to be false. And that's going to come up in a couple questions like this next one. Blank measures the average kinetic energy of a substance, and that's what temperature is. Temperature is really just giving you an idea of how fast the particles are moving. If you have two different beakers of water, one of them's at 95 degrees Celsius and one of them's at 25 degrees Celsius. Well, the 95 degrees Celsius beaker, the water in there, the molecules are moving much faster. And that's really all temperature is, average kinetic energy. It's measuring average kinetic energy. Heat is, now there's a little bit of vocab with this. Intensive means it's independent of amount, and extensive means if you have a different amount you will get a different result. And heat is extensive and temperature is intensive. And so if you have two different beakers of water and they're both at 75 degrees Celsius, well, they have the same temperature. Their particles are moving at the same speed. Now if you have two different beakers of water and one of them has a lot of water and one of them only has a little bit of water and they're both at, say, 75 degrees Celsius, well, the beaker with more water has more heat associated with it because heat depends on amount. Heat is extensive, temperature does not depend on amount. Blank reactions absorb energy, and that would be endothermic. And if you're going to draw an energy diagram for this where we had enthalpy on the y-axis and the reaction progress on the x-axis, an endothermic reaction will look something like this, where you have the reactants on the left and the products on the right. One of these energy diagrams is always from the chemicals point of view. So the reactants have less stored energy than the products do. So what that's telling you is that those chemicals are absorbing energy and storing the energy in the bonds of the products. Or if you watch this after we have done the equilibrium chapter where we have like cover a catalyst and stuff like that, you might have it drawn a little more like this. It's really showing you the same thing. The reactants have lower enthalpy, the products have higher enthalpy for an endothermic reaction. So in an endothermic reaction, if the chemicals themselves are absorbing energy, the place where they get that energy is from the surroundings. So this is a reaction where you would see the surroundings decrease in temperature, because remember, when you measure temperature, you measure the surroundings. And the way you can think about it is there's always 2 points of view. You have the substances or the chemicals point of view, and you have the surroundings point of view. And in the heat chapter, we see that those things are always opposite. So if the chemicals are absorbing heat energy, the surroundings lost heat energy, and vice versa. Now we also did a little bit of stoichiometry type problems in the heat chapter. So in this one it says you have 4 moles of ammonia reacting with 5 moles of O2. Goes to 4 moles of nitrogen monoxide, 6 moles of water. It gives you a delta H. That's a negative 1170.0 kilojoules. And it's saying how much heat is transferred when 14.9 grams of ammonia, which is an H3, react. Now this is going to come up in another problem. But if you see a negative delta H, that is exothermic. It's telling you the chemicals release the energy to the surroundings. So this is one where you would feel the surroundings get hotter. And what you want to do is start off with the number you're given, 14.9 grams of ammonia. Because if you have 4 moles of ammonia, it would release 1170 kilojoules. Well, now it's saying, well, you don't have 4 moles, you only have 14.9 grams of ammonia. So you're going to end up getting a different heat associated with it, because remember, heat is extensive. It depends on amount. So now what we want to do, since you start off with grams of ammonia, you put that on the bottom. 1 mole of ammonia goes up top. Nitrogen off the periodic table is 14.0 grams. You get another 3 from the hydrogen, so that's 17.0. So that's a mole conversion, just like we've always done. Grams of ammonia cancel out. Now we could put moles of ammonia on the bottom. And the way I think about this step, it's kind of like a modified mole ratio. We want to go from moles to kilojoules. The only spot kilojoules is listed is up here. It's negative 1170.0 kilojoules. And if you go to the chemical reaction to get the heat term, then that's where you get the number for the moles, because Remember, heat depends on amount, so it's 4 moles of ammonia is associated with that much heat. Now moles of ammonia can cancel out, and if you do this math and round it off to the right number of significant digits, you should get 256 kilojoules released. Now the other way you could do it, you could also give the answer as just negative 256 kilojoules. They're released and the negative mean the same thing. Heat is a product. If you were going to write this reaction out, not in delta H term as a thermochemical equation, you would have this product plus 1170.0 kilojoules, because when the reaction's exothermic, heat is a product. It's released. So just like these products are released to the surroundings, that gets released to the surroundings too. Now this next problem is a Hess's Law problem, and these usually are a little longer. It's giving you these 3 sub-equations, and it's saying and it gives you the delta H for each one, and it's saying calculate the delta H for this overall equation. So what you have to do is look at this overall equation, and I really just work left to right. First thing you're looking at is this 2-carbon, and that's a reactant. The only spot carbon comes up in these sub-equations is in this first one. Now it's on the correct side, it's a reactant, and we want it as a reactant, but it doesn't have this coefficient of 2 in front of it. So what we have to do is multiply that sub-equation by 2. So I'm going to rewrite this down here just the same way. You have 2 carbons. I'm leaving out these symbols just to make it a little less cluttered when I do it. Plus 2O2 goes to 2CO2. And now this delta H term, I have to make sure I multiply that by 2 also. No, I didn't flip it or anything, so the delta H stays the same. So that delta H is now negative 787 kilojoules. Alright, now the next thing that we look at is H2. The only spot it shows up is right here. Now we want it as a reactant, it's shown as a reactant, the coefficients match, so everything's good on this one, so I'm writing NC for no change. So I could just rewrite that one. H2O. Since I didn't change anything, the delta H term ends up being exactly the same. Negative 285.8 kilojoules. The next thing in line is C2H2. Only spot it shows up is right here, but there's 2 things wrong with it. One, I want it as a product, but it's shown as a reactant, so I know I have to flip this equation. The other thing is I want a coefficient of 1, but it's shown with 2, so I also have to divide it by 2. So I have to do 2 things there, flip it and divide it by 2. Now when you divide by 2, remember you're only looking at the coefficients with that. So 4CO2 becomes 2CO2. The 2H2O becomes H2O. And now we have C2H2, and this 5O2, I'm just going to write it as 2.5O2. If you prefer to use fractions, go for it. Either way, it means the same thing. Now for the delta H, since I'm flipping it, it now becomes positive, and I have to divide it by 2, so I get 1,299.4 kilojoules. Now I want to double check my work just to make sure I get this overall equation back. So anything that's on opposite sides cancels out. So like this 2CO2, I have it as a product here and a reactant here. The O2, I have 2 plus another half, so that's a total of 2.5 on the reactant side, and here's 2.5 on the product side. So all of that cancels out. The 1 mole of H2O cancels out. The only thing that's left is the 2 carbons and the hydrogen on the reactant side and the C2H2 on the product side. I get this equation back that I was looking for, this one. So that means I did all my work right. So now delta H, I could just add everything up. And when I do that, I should get 226.6 kilojoules. Now in this example, it didn't come up. Sometimes when you're looking at this overall equation, you might see something that shows up in more than one sub-equation. And if that happens, you just skip that in this overall equation and just move on to the next one, because what that's telling you is that that thing would just cancel itself out anyway. Didn't come up in this problem, but again, if you are looking at something and it shows up in more than one sub-equation, just skip it and move on to the next thing and it will work itself out. All right, for this next one, how much heat energy is required to raise the temperature of 789 grams of acetic acid from 25.0 to 82.7 degrees Celsius? Specific heat of acetic acid is 2.05 joules per gram degree C. So if it's asking just flat out heat, the equation is Q equals mass times specific heat capacity times delta T. The mass is given in the problem at 789 grams. The specific heat capacity is 2.05 joules per gram degree C, and get into the habit of writing the units in the problem because it's going to let you know if you're setting it up right or not. And then the delta T, you always do final minus initial. So you're doing the 82.7 degrees Celsius minus the 25.0 degrees Celsius. And what I think works well is to do the subtraction first. That gives you 57.7 degrees Celsius, and now you can multiply all of this stuff out. When you do, the grams cancels out, the degrees C cancel out, and what you'll be left with is joules. So 789 times 2.05 times 57.7, you get a pretty big number there on the calculator. It's 93,326, and I think it's 0.865 or something like that. Now, what I did in a lot of these examples is I just converted it to kilojoules just because it's a little easier to work with. All of these things have 3 significant digits. So you really have 2 options. You could write your answer as 93,300 joules, or you could write it in kilojoules. And a lot of times with a number that big, people just tend to go to kilojoules. All right, that's what this one is, 93.3 kilojoules. All right. This is getting back into a little multiple choice kind of question here. Exothermic reactions have a blank delta H. Now if you have exothermic, enthalpy is on the y-axis, reaction progress is on the x. What happens is exothermic, the reactants have more stored energy than the products. A good example of this is burning a match. The match has that phosphorus chemical on the end of it, and it has a lot of stored, potential chemical energy. And when you burn it, you are releasing that energy from those bonds, and that's what's going to the surroundings, which is why you feel heat given off. Now, again, if you're used to the equilibrium, including like a catalyst activation energy, it would look a little more like that. But it's really doing the same thing. The reactants have a higher enthalpy than the products. And if you think about that match, the act of striking the match is what it is, the energy it takes to get over this activation energy here. And then it burns pretty quickly after that. So these reaction diagrams are always from the chemical's point of view, and anytime you do delta, you do final minus additional. So you do a small number minus a big number. That is going to give you a negative delta H, and that's how it's always going to be for exothermic, negative delta H. So an endothermic reaction, remember this is one that would then look like this, will cause it's going to be a decrease in temperature, so it's not that or that, because the substance, meaning the chemicals, and what they do is absorb heat energy. You see how they're going up? So what you should end up getting is this. So delta H for endothermic is positive, but delta T is negative. And remember, it's because delta H is from the chemical's point of view, and delta T is from the surroundings point of view. So if one's going up, the other one's got to be going down. So pay attention to whether it's talking about the chemicals or the substances or the surroundings, and either temperature or enthalpy, right? Because they all end up being the opposite of each other, really. And number 10, what is specific heat? So if it's asking specific heat, what you should end up getting for units is joules per gram degree C, because specific heat is the amount of heat, which is joules. So the amount of heat it takes to raise 1 gram of a substance by 1 degree Celsius. So what you get is Q over M delta T. And let's see, it gives you the heat is 11.1 joules. It gives you that directly. It gives you the mass is 4.11 grams. and it actually just flat out gives you delta T. It doesn't even give it a final minus or final and initial.